Okay guys, in this next video we are going to talk about reaction yields, and I'll introduce the concept of a theoretical yield and the idea of a limiting reactant and actual yields so that we can calculate percent yields. The idea of a limiting reactant is that when you have a reaction, you don't always combine the reactants in their stoichiometric proportions. For example, some reactants might be completely consumed, but other reactants you might have some left over. And so as a consequence of that, the amount of product that you can make is limited by the reactants that are totally consumed. And the excess reactant is whatever's left over of the reactants after the reaction has completed. And so the analogy here is given in this cheese sandwich diagram. And so the chemical equation for a cheese sandwich is that one cheese sandwich is equal to 2 slices of bread plus 1 slice of cheese. So suppose that you had 28 slices of bread and 11 slices of cheese. The number of cheese sandwiches that you can make is going to be limited by the pieces of cheese that you have in this case, right? Once you start making the sandwiches, after you run out of cheese, you won't be able to make any more cheese sandwiches, and you're going to have some excess bread left over. The situation is analogous to what we have in chemistry. In this reaction here, we've got hydrogen plus chlorine gives us hydrogen chloride. And let's suppose that you had 4 molecules of chlorine and 6 molecules of hydrogen. The amount of hydrogen chloride you can make is going to be limited by the number of chlorine molecules you have available in this case. And so each molecule of chlorine can produce 2 molecules of hydrogen chloride. And so since you have 4 molecules of chlorine gas, you can have 8 molecules of hydrogen chloride, but there's going to be some leftover hydrogen, 2 leftover molecules as we see here. Okay, and so that's the idea of a limiting reactant. The chlorine in this case limits the theoretical yield of the hydrogen chloride, right? So it's the maximum amount of hydrogen chloride we can make is limited by the amount of chlorine we have. Hydrogen is the excess reactant in this case. We also have the concept of an actual yield. So the theoretical yield is the maximum amount of products you can make given your reactants. However, reactions don't always go as planned. For example, you could spill some of your reactants, okay, so you can't make as much product in that case. Also, reactions just stop before going to completion, and that's a topic that will be addressed in the second course of general chemistry when you study the topic of chemical equilibrium. Suffice it to say that the actual amount of product you make is always less than the theoretical amount that you can make. And so you can calculate what's called a percent yield. You take the actual yield of your product, the amount in grams or the amount in moles, and divide it by the theoretical amount in grams or moles, and multiply that by 100. And so a reaction that gives you a 99% yield is a good thing. That's an efficient reaction. However, you may encounter reactions that are not very efficient and will only give you a 10% or worse yet, a 1% or a 0.1% yield, which would be a bad reaction. And so we're going to learn how to calculate theoretical yields and percent yields using stoichiometry. So here's an example. We've got zinc reacting with hydrochloric acid to produce zinc chloride and hydrogen gas. It says if we've got 0.3 moles of zinc and we combine that with 0.52 moles of hydrochloric acid, how many moles of hydrogen gas are produced. Okay? Now this problem is different than the ones that we looked at in the last video. In the last video, they gave you an amount of a reactant and asked you to calculate what is the amount of product you can make. Here, they're giving us the amount of two reactants. Okay? And so that's the key feature of a limiting reactant problem. They give you the amount of both reactants, and then they ask you to figure out how much product you can make. And so one of these two reactants is going to be the limiting reactant. At this point, we don't know which one it is. And so what we need to do is to calculate what is the theoretical yield coming from the zinc, and then calculate what is the theoretical yield that you could get from the HCl. Whichever theoretical yield is smaller is the true theoretical yield. Okay, so let's work this problem out. What we're going to do is we're going to take the moles of zinc, and we are going to convert that to moles of hydrogen that can be produced. And I'm going to put the calculation right here, and then we're going to do a second calculation. We're going to convert moles of HCl to moles of hydrogen, and then we're going to compare those two numbers to see which one is smaller. So let's start with the zinc. 0.30 moles of zinc. We use the stoichiometric coefficients to convert from moles of zinc to moles of hydrogen. It's a 1-to-1 ratio. So 1 mole of hydrogen for every 1 mole of zinc that reacts. That's going to give us our number. And I'll set up the HCl calculation as well. 0.52 moles of HCl. Here the stoichiometric ratio is 2-to-1. So it's going to be 1 mole of H2 produced for every 2 moles of HCl that react. And that's going to give us another number. So let's calculate those numbers. Well, this is an easy one. 0.52 divided by 2, 0.26 moles of H2. We see that the 0.26 moles is smaller than the 0.30 moles. Since this number is smaller, that identifies the HCl as the limiting reactant, and the zinc is the excess reactant. Okay? So all of the HCl is going to be consumed first, and then we're going to be left over with some extra zinc. Okay. So the answer to this question, the theoretical yield, is 0.26 moles of H2. That's the maximum amount of H2 that we can make, given these two amounts of reactants. Here's another example. Let's go ahead and work this one too. So in this reaction, we've got 0.15 moles of aluminum and 0.35 moles of HCl. They want to know how many moles of the aluminum chloride can be prepared. Well, we need to do the same thing that we did in the last problem. We're going to convert the moles of aluminum to moles of our product. And we'll do the same thing for the HCl. Moles of HCl to the moles of product. 0.15 moles of aluminum. Here we have a, 2-to-2 ratio. So 2 moles of aluminum chloride for every 2 moles of aluminum that react. For the hydrogen chloride, we've got 0.35 moles of HCl, and then it's a 2-to-6 ratio. So we've got 6 moles of hydrogen chloride in the denominator. So we'll calculate this number. So this is just 0.15 moles. And and then 0.35. That gives us 0.12 moles of the aluminum chloride. And we see that the smaller number is the 0.12. So that identifies the hydrogen chloride, again, as our limiting reactant. The aluminum is our excess reactant. And then the theoretical yield is this number right here, the 0.12 moles of aluminum chloride. So that's the answer to this question. This one is more elaborate. It's the same idea, but there's more involved in this problem. So let's look at this one. So we have acetaldehyde reacting with oxygen to give us acetic acid. And this time, instead of giving us moles of reactants, they've given us grams of the two reactants. We still solve the problem in the same way, except that we have to do a gram to mole conversion before we can calculate the two theoretical yields. Okay, so in the end, they want us to know what's the theoretical yield of acetic acid in grams. Before we get going with the actual calculations, we need the molar masses of all of the species involved here. So the molar mass of the CH3CHO, we've got 2 times 12.01 plus 4 times 1.01 for the hydrogens, plus 16. So we'll get that. We also need to do the oxygen, which is just going to be 32 grams per mole. And we're going to need the acetic acid. So that's going to be 2 times 12.01 plus 34 plus 2 times 16. We'll get those numbers. All right, so we've got our molar masses established, and now we are going to do the following conversions. We're going to take the grams of the acetaldehyde, and we're going to convert it to moles, and then we're going to convert that to moles of acetic acid. We'll do the calculation right here. And then we're going to do the same thing with from the oxygen. So we'll take the grams of O2, we'll go to moles of O2, and then to moles of acetic acid. And then we're going to need to compare those two numbers. Okay? So we've got 20 grams of the acetaldehyde. The molar mass is 44.06. And then from the reaction, there are 2 moles of acetic acid for every 2 moles of the acetaldehyde. We'll do the same thing for the oxygen, so I'll set that up. 10 grams. This time we divide by the molar mass of oxygen. Now we multiply by the stoichiometric coefficients, 2 moles of acetic acid for every 1 mole of O2. And we'll do those calculations. So I'm getting 0.454 moles of acetic acid And then we'll do the calculation for oxygen. I'm getting 0.625 moles of acetic acid. And so we'll compare. Okay, the 0.454 is smaller than the 0.625. That tells us that the acetaldehyde is the limiting reactant over here. And the oxygen is the excess reactant. So our theoretical yield in moles is 0.454. However, they want the theoretical yield in grams. So we need to do a calculation. We need to convert 0.454 moles of acetic acid. We need to convert that to grams by multiplying by the molar mass. And so this number is going to be the theoretical yield. And I'm getting 27.3. That's our theoretical yield right there. So that's the answer to part A. Now the follow-up question, part B, how many grams of the excess reactant remain after the reaction is complete? So we started with 10 grams of oxygen. Now some of that oxygen is going to react to produce this many grams of acetic acid. And if you take the amount that reacts, the amount of oxygen that reacts, and subtract it from the 10 grams, then that's going to be the amount of oxygen left over. So what we need to do is we need to take the theoretical yield of acetic acid in moles and back calculate the moles of oxygen, or rather the grams of oxygen that react. So we are going to go from the moles of acetic acid we're going to convert that to moles of oxygen, and then we're going to go back to grams of oxygen. That's going to be the amount of oxygen consumed, which we will subtract from the initial amount of oxygen. Okay, so we'll take that 0.454 moles of acetic acid, and we're going to convert it to moles of oxygen. So from the stoichiometric coefficients, 1 mole of oxygen will react for every 2 moles of acetic acid that are produced. And then to get the grams of acetic acid that were consumed, we multiply by the molar mass of oxygen. And that gives us 7.26 grams of O2. Keep in mind, that's the amount that was consumed. To get the amount of oxygen in excess, so the excess O2 will be the initial O2 minus the consumed O2, which is what we just calculated. So it will be 10 grams minus 7.26 grams. Or 2.74 grams. So that's the answer to part B. That's the amount of oxygen that remains after the reaction is complete. Okay, so this one was quite involved. Here is another one that's very similar that you can practice this type of calculation. So you can calculate the theoretical yield of the zinc sulfide, and then you can also figure out, of the two reactants, which one's the limiting reactant, which one's the excess reactant, and then you can calculate the amount of the excess reactant that will be left over at the end. I'm going to turn to a different type of problem. This one involves the actual yields and the percent yields. And so we'll get some more practice with our limiting reactant calculations. So here we've got methanol reacting with carbon monoxide to produce acetic acid. We've got 15 grams of methanol and 10 grams of carbon monoxide that are reacting. We want to find out what's the theoretical yield of the acetic acid, and then if the actual yield of the acetic acid is 19.1 grams, what would be the percent yield of the acetic acid? So we'll do the limiting reactant problem again. So in this case, we're going to need the molar mass of the methanol, the molar mass of the carbon monoxide, and the molar mass of the acetic acid, which we've already calculated. I believe it was 60.06 grams per mole. The carbon monoxide is 28.01 grams per mole, and the methanol (32.05 grams per mole). We need these numbers to start with. Okay, and so what we'll do is we're going to convert from grams of methanol to moles of methanol, and then we'll go to moles of acetic acid. We will also do the grams of carbon monoxide to moles, and then to moles of acetic acid. Right? And those will be the two numbers that we compare to identify which is the excess reactant, which is the limiting reactant. So, given 15 grams of methanol, we will divide by the molar mass. Then we will use the stoichiometric coefficients, which are 1 to 1, to convert that to moles of acetic acid. We'll do the same thing for the 10 grams of carbon monoxide, but we'll divide by the molar mass of the carbon monoxide. And again, it's a 1 to 1 ratio coming from the reaction. So we'll see what numbers we get. So we see that the number of moles of acetic acid generated from the carbon monoxide is smaller than that generated from the methanol. So this is the theoretical yield in moles of the acetic acid. The 10 grams of carbon monoxide is the limiting reactant. The 15 grams of methanol is the excess reactant. Okay. We're going to calculate the theoretical yield of acetic acid in grams. So we'll take the 0.357 moles of acetic acid, and we're going to multiply by its molar mass. We get 21.4 That's the theoretical yield of acetic acid in grams. Now the problem says if the actual yield is 19.1 grams, what would be the percent yield? So the percent yield is the actual yield divided by the theoretical yield times 100. I'm getting 89.3%. No, it should be 89.2%. So there's the percent yield problem. Well, we're going to go ahead and stop this video here, and we'll talk about volumetric and gravimetric analysis and combustion analysis in forthcoming videos.